For our first example, we're going to evaluate the integral of 2x plus 1, and that's between x equals 3 and x equals 4. Now for all of these examples that we're going to do in part 1, I'd encourage you to have a look at graphing them and seeing what the area under the curve looks like, but we'll just stick to the algebra. Now before we do that, just a quick recap. Remember, we are finding the antiderivative, so we need to do the opposite process to differentiation. So we know for any x to the power of n that if we differentiate this, algebraically what we do is we bring the power out the front and then we drop the power by 1. So if we are going to go the opposite way, and if we are going to integrate some x to the n with respect to x, then we need to add 1 to the power and then put it over that power. And it can always help when you do an integral to just differentiate your answer and see if you get back to what you started with. So if we were to differentiate this, the n plus 1 is our power that would come out the front. Okay, so let's just write that. So the n plus 1 would come out the front. We can see that that would cancel with the n plus 1 that's already on the bottom. And then we need to subtract 1 off the power. Now plus 1 minus 1 means they would cancel, and so we would just be left with x to the power of n, which is what we started with. So that's great. So if you ever need to, just differentiate your answer and see if you get back to what you originally started with. So let's first focus on the 2x. We are going to raise the power. So currently it's x to the power of 1. Okay, there's like a 1 here. So we're going to raise the power, which takes us to 2. But then we are going to put it over this power. Now let's focus on the 1. There's no x there at the moment, is there? But we could think of it as like an x to the power of 0. And so when we raise that to the power of 1, we get one lot of x to the power of 1 over 1. Now, of course, both of these terms can be simplified, and as you get better at it, you're more than welcome to jump straight to x squared for our first term, and then x for our second term. And let's just take a moment to think about differentiating x squared. The 2 would come out the front, we'd drop the power by 1, so we would get 2x. And if we differentiated x, well, that just leaves us with 1. So this is correct. When we're dealing with definite integrals that have these x values, it's common for us to use square brackets around our antiderivative function, and then to place these x values here, just to show that we are still dealing with a definite integral. And now is where we use the fundamental theorem of calculus. Now what's that? It sounds pretty crazy. Fundamental theorem of calculus. Well, all that is what we wrote down before. So not that crazy after all. So let's apply that here. We're going to sub in our b value first, and then our a value, with a minus in between. So we have 4 squared plus 4. That's what we get when we substitute 4 in place of x, minus, and now we're going to substitute in 3. 3 squared plus 3. Working this out, we see that 4 squared is 16, plus another 4 is 20. 3 squared is 9, plus another 3 is 12. 20 minus 12 gives us 8. And that is the answer to our integral. So if we were finding the area under this function, between 3 and 4, it would be 8 square units. However, since we are just finding the value of the integral, we just write the number 8. Let's go on to question 1b. Evaluate the integral of negative 3x squared between 0 and 2. So let's raise the power by 1 and then put it all over that power. Simplifying, we can see that this gives us negative x cubed. Applying the fundamental theorem of calculus, we're going to substitute in the value of 2. Now I'm using brackets here just to be careful because of this negative out the front. And then I do need to subtract f of 0, however that's just going to be 0. Right? We know that negative 0 cubed is 0. So 2 cubed is 8, but then we have this negative out the front. So our answer to this integral is negative 8. Now does this seem a little bit funny? Why have we got a negative out the front? Especially when we think that this relates to area, how do we have such thing as negative area? Well, for this one we will consider what the function actually looks like. Negative 3x squared is just an upside down parabola. Okay, it's got its vertex at the origin, and compared to our stock standard parabola, it's stretched by a factor of 3. And we are after this area here. That is the area between the curve, the x-axis, and x equals 0 and x equals 2. And notice how this area lies below the x-axis. So that's actually the link. So the area itself is positive, because area has to be positive, but the integral value is negative. Time for example C. Evaluate the integral of 2x minus 3 all over x cubed between x equals 1 and 2. Now this one's starting to look a little bit harder. On first glance, we might associate this to something to do with like the quotient rule with differentiation, but how are we going to undo that through anti-differentiation? So the best way to approach these is to split the fraction. So commonly we're used to combining fractions together, but in this case, let's split the fraction. So before we even attempt to evaluate the integral, we're going to split this into 2x over x cubed minus 3 over x cubed. And then we can simplify the first term. The x on the numerator will cancel with one of the x's on the denominator, and so we get 2 over x squared minus 3 over x cubed. Now, you might be looking at this and thinking, this still doesn't look that easy. But if we use what we know about negative indices, then we can turn these into sort of the x to the n that we were dealing with previously. So this 2 remains as a 2, nothing changes there. But this x squared on the denominator, using negative indices, becomes x to the power of negative 2. Likewise, we have our minus still, and our 3. And then x cubed becomes x to the power of minus 3. And now we can apply the process of raising the power by 1 and putting it over that power. So our first term, we have 2 x. Now we're raising this. So minus 2 plus 1 gives us negative 1. And then we're going to put it over that new power. And secondly, we have minus 3x raising the power by 1 gives us negative 2 over negative 2. And so there's a little bit of tidying up to do here. So let's give ourselves a bit more room. Now it's up to you whether you change the form back to the fractional form. That's what I'm going to do, but you don't have to do that. So we have negative 2 on the top, and then this x to the minus 1 means that x goes down the bottom. Here we have a minus and a minus, which will turn into a plus. We have 3 on the top. There's a 2 on the bottom, and this x to the power of minus 2 becomes x squared on the denominator. So personal preference as to whether you keep the negative indices or the fractional indices, just do what works best for you. And now time to substitute in these values of x. So first of all, we have x equals 2. And then we're going to take away the result when we substitute in x equals 1. And now time to calculate. We have negative 1 plus, this is 8 on the bottom, so we have 3/8, minus, and in the second brackets, we have negative 2 plus, and on the bottom here we have 2, so this is 3 on 2. A few lines of working for this one. But we're really just up to this last step where we're mucking around with the numbers. So if we combine minus 1 plus 3/8, we get negative 5/8. Minus, and when we look at minus 2 plus, now this is 1.5, right? 3 on 2 is 1.5. So minus 2 plus 1.5 gives us negative 1/2. So we have minus 5/8 plus, the two minuses make a plus, and just to create a common denominator, I'm going to express 1/2 as 4/8. And finally, adding this together, we get minus 1/8. And that's as simple as we can get it. Okay, example 1D. Evaluate the integral of the cubed root of x between 1 and 8. So another one that looks hard initially, but if we use our knowledge of indices, we can turn this into a form that we're more familiar with. So how else can we express the cubed root of x? Well, this is where we can use fractional indices. The cubed root of x is simply x to the power of 1/3. And now that it is in this form, we can raise the power by 1. So x to the power of 1/3 plus 1. That's 1 1/3 or 4/3. And I would recommend that you use this in proper form. And now we want to put it over that number. So we're putting it over 4/3. Now that's a little messy, having fractions within a fraction. Remember, whenever we have this case of some fraction divided by another fraction, it might help you to write it out like this. X to the power of 4/3 is divided by 4/3. When we divide by a fraction, that means that we can do a times and flip. So rather than thinking of it as divided by 4/3, we are really timesing this, x to the power of 4/3, by 3/4. And so you might like to write your answer like this. Okay, now once again, it's up to you if you want to keep it in this form, the fractional form, or if you would like to go back to this form with the radical signs. So that would be 3 times, now x to the power of 4/3. There's two different ways we can write that. We can write it as the cubed root of x to the power of 4, or we could write it as the cubed root of x all to the power of 4. And the way in which you write it can help you do computation a little bit quicker in your head as we keep going. So remember, we want to substitute in the values of 8 and 1. If I substitute 8 in here, I mean, I know I can go to the calculator, but I've got to work out 8 to the power of 4. So that's why I'm actually going to use this second way of writing it when I substitute my values. So first of all, we have 3 times the cubed root of 8 all to the power of 4, and that's over 4. And then I'm going to subtract the answer I get when I substitute in 1. So the cubed root of 1 all to the power of 4 over 4. See, the cubed root of 8, that's just 2. So I can write this as 3 times 2 to the power of 4 over 4. And this one's nice. The cubed root of 1 is just 1. And 1 to the power of 4 is going to be 1. So that's nice and easy. And now this is a little bit nicer to deal with rather than 8 to the power of 4. So 2 to the power of 4, that's 16. But 16 over 4, well, that's just 4. So I've got 3 times 4 is 12, minus, and then this is just going to be 3/4. And so my final answer to finish off is 12 minus 3/4, which is 11 and 1/4. Alright, final example, example 2. This one's a little more practical and involves velocity and displacement of a particle. The velocity of a particle is given by v equals 8t cubed minus 3t squared plus 6t plus 1, and that's in centimeters per second. We need to find the change in displacement in the first 3 seconds. So the first thing to remember is that velocity, by definition, is the change in displacement compared to the change in time. So when we talk about so-called instantaneous velocity, it's the derivative with respect to time of displacement. X is displacement. So if we are deriving x to get velocity, so deriving displacement, then if we integrate velocity, we go back to displacement. So we want to integrate this in order to find the displacement function. So the displacement function, x, is the integral of this velocity function, 8t cubed minus 3t squared plus 6t plus 1. And in this case, we're integrating with respect to time. So we have a dt at the end. Now, do we have any values for t to put on our integral symbol? Well, yeah, we are after the change in displacement in the first 3 seconds. So from time equals 0, when this particle sets off, up until the 3-second mark. So now that we've set up the question, we just need to integrate. Let's do it term by term. 8t cubed. If we raise the power, that gives us a power of 4, but 8 over 4 is just 2. Now just quickly double check this. If you derive it, the 4 comes out the front. 4 times 2 is 8. Drop the power by 1, that's 3. Next one, we are going to raise the power by 1, so that's 3. But when we put it over that 3, it'll cancel with this one. So we simply have t cubed. Plus, up the power by 1, so we'll go to a squared. But when we put it over 2, 6 over 2 gives us 3. And finally, plus 1 just turns into t. This is between 3 and 0. Now when we substitute in, once again, when we substitute in the 0, that's just going to give us 0 at the end here. So we're really just worried about what's happening when we substitute in t equals 3. So we have 2 lots of 3 to the 4 minus 3 cubed plus 3 lots of 3 squared and plus another 3. Calculating all of this, we get 165. So in terms of the question at hand, what this means is the change in displacement in the first 3 seconds is 165 centimeters. And that finishes off all our examples. Good job.